So now we have made our vaccines, we have induced the Th1 response, but how do we know whether this response is protective or not? And this is one of the biggest enigma in the field of vaccinology, that is the correlates of protection. And this is the second step. We have a vaccine, but how do we know it protects? For many viruses, the antibodies serve as a correlate of immunity. For example, the vaccination against rubella, there the serology and the antibodies induced by the vaccination is deemed to be sufficient to say that the vaccine is providing a protection. On the other hand, for HIV, we know that there are plenty of antibodies in HIV-infected persons, and the presence of antibodies itself is not clearly a correlate of immunity or protection, since the infected individuals are not protected while they have the antibodies. The lack of known correlates of immunity or protection is a significant barrier in the HIV vaccine research. There is evidence that some highly exposed individuals can develop resistance to HIV infection, suggesting that immunity and therefore a vaccine is possible. However, without knowing the correlates of immunity, the scientists cannot know exactly what sort of immune response a vaccine should stimulate. The only method to measure how effective an HIV vaccine is to do a large phase 3 trial in which the clinical outcomes, so infectious disease, is measured, and not any kind of laboratory outcome from the vaccination itself. This image is suggesting several different factors that can be measured after immunization, which may correlate with the protection to some degree. For example, an enhanced inflammatory innate immune response in the beginning during vaccination may be a sign of a more efficacious vaccine. Also, the cytokines produced by the T cells may be indicative of that these T cells are more effective in the protection. But all of these measurements are proxy measurements, and not until the individual or the animal is challenged with the infection can we for certain know whether a vaccine is protecting or not. So, as I mentioned before, the most important part with the vaccine is the immunological memory. And the function of the immunological memory is that the small pool of memory cells are created upon the first exposure of the antigen. This is a fairly slow process. As you see here in the primary antigen X response, we have a peak at around 2 weeks. This response then dies down to a quite low level, and sometimes after a prime you cannot detect antibodies and it's hard to detect even T cells. And this is because the memory pool, once the antigen is completely gone and the effector cells are gone, is very small. Therefore, almost all vaccination strategies are depending on a booster, and the booster causes a very rapid expansion of the memory cell, and these memory cells then give rise to more effector cells than in the first time. And also, as you remember from the T follicular helper slide, it causes the replication of the B cells, which then give rise to plasma cells. So in the boost, the second peak, you see that there is more plasma cells and more antibodies, and here the response is faster. A typical secondary response against antigen only takes a few days, 5 days, while the primary response peaks after 2 weeks. So here you see that there is, in the second boost, we have also included antigen Y together with the boost with antigen X. Since the antigen Y has not been seen before, the response against the antigen Y is not benefiting from the booster effect on the response of antigen X. A new antigen introduced will always behave like a primary response. So therefore, the antigen Y here in this case will start to give rise to a slower response than for the antigen X, which was included in the initial immunization. So, also worth mentioning here is that at week 10, when the antigen is gone and we have again returned to a position where memory pool, this memory pool is larger, and this is true both for the B cells and for the T cells. So we have many more memory B cells after a boost with the same antigen than what we had before. And it is the number of memory B cells rather than the plasma cells, which will determine the ability to fend off a bacterial or a viral infection, since the memory B cells can rapidly, within the matter of days, produce very large amount of plasma cells and therefore antibodies. So now we will focus a little bit more on the adjuvants. The ideal adjuvant does not exist, but several adjuvants are constantly in development, and adjuvant development is a really central part to vaccine development. It is worth mentioning here the different types of requirements that the industry and the regulatory bodies have on the ideal adjuvant. So firstly, it should make the vaccine more cost efficient, and that means that fewer doses of the vaccine should be required, as opposed to a weak adjuvant, which will require several boosters. The adjuvant should induce the effective innate immune signals, including danger signals. And what we know today, the effective immune signals is probably must include a TLR. Immune modulatory capacity, that means a good capacity to steer the T helper cells towards the direction which is required, and that is then mainly towards the Th1 direction. The adjuvant should help producing highly specific antibodies, and this means that the adjuvant should not contribute to denaturing the protein, if this is how the vaccine is delivered, or in any way disturb the native folding of the antigen. So it should deliver an antigen-specific clonal expansion. That means that the T cells and the B cells found in the vaccinated individuals should have expanded to a large degree. That means that there should be, even after one immunization, double amounts of T and B cells. The T cells should have a cytotoxic effect. That means that the T cells should have a Th1 phenotype, and they should be able to kill target cells expressing the antigens in the vaccines. We need the memory, the long-lasting adaptive immune responses, and we want to be able to boost the effect of the antigen. So the more effective the adjuvant is, the less antigen is required. Sometimes the antigen manufacturing is very expensive, and therefore you want to reduce the dose of the antigen as far as possible, and with a really good adjuvant this may be possible. So here is a list of adjuvant in actual use from the CDC. As you see on top, aluminium is listed, and we have carelessly referred to this as alum, but as we'll see, this is not really the correct terminology. There are certainly different types of aluminium salts and crystals used as adjuvants in many different vaccines and since the 30s. If you zoom into the right column of the aluminium section, you will probably recognize a lot of vaccines that use this aluminium. The ones that I immediately recognize, which has been given to my children, is the Prevnar, which is a pneumococcal vaccine. Also the HPV Gardasil 9 uses an aluminium, but many of these vaccine names are also typically American. The AS04 adjuvant is a combination of aluminium salt and monophosphoryl lipid A, which is a derivative of LPS, and you see the molecular structure here on the left. MPLA, then, as it's called, can be produced either by hydrolysis of native LPS or by a synthetic production line. MPLA is much less toxic than LPS, which I mentioned before. The TLR4 triggering via LPS can be very dangerous, but it still activates the TLR4. So the toxicity profile of this molecule is much, much better than the LPS. So it's also used in several different formulations. Then we come to the oil in water emulsions. This is what we're going to talk about in the following slide, and I'll go into how that works. Then there are two more unusual adjuvants. One of them is based on a soap bark tree component called QS21, which is a mild detergent, which is used for forming liposomes. Also, CPG has been used in hepatitis B vaccination, but this is not a very common adjuvant for the moment. Then at the bottom of the table it says no adjuvant, and this is of course not true, because these are viral vaccines and they do viral replication, so they basically carry with them their own adjuvant. And the own adjuvant is that they cause ligation to the TLRs and activation of the RLRs, the Rig-like receptors inside of the cells, and therefore they cause cytokine production and also cell death, which provides the antigen for cross-presentation.